you understand current valves, I mean water valves, you should understand transistors, right? So bipolar, bi meaning two, and what it basically means, it has two junctions. So a diode would be a unipolar device, and then a bipolar device means it's got two junctions, two p-n junctions. And so if we do that, we can arrange them either like this. We'll see. So I could come over here and place an N between two P's, or I could come over here and place a P between two N's. And so this got an arrangement. We refer to it as a PNP transistor, BJT. And this one we'll refer to, of course, as an NPN BJT. And we have two categories of transistors. We have BJTs, and then we have field effect transistors. And of course, we refer to these as FETs. And each one of them's got advantages over the other. Your cell phone, due to the lower current drain and low power demands, just about all the transformers in your smartphone is going to be FETs because it's not a real high power demand. So your bipolars are used primarily for a lot of high voltage, high power commands, and then your FETs are used a lot for low voltage, low current demands. So basic water valve, everybody understand that? So we got a pump. So this will be our voltage supply, our power supply. And then we use this guy right here. So this is what your BJT is actually doing. But instead of controlling the flow of water, it's controlling the flow of current. This makes sense. Now, what do we use to control the flow of the water? Well, we use these things called valves, right? And what can we do with that valve? We can turn it all the way off, right? Or we can turn it all the way on, or we can operate it in the center. But if you turn the water all the way on and you try to control the flow with your hand, you can't do that, right? So what we do is we get a mechanical advantage out of the valve itself. Usually they use a screw that's got narrow threads on it, and it acts like an incline. So it allows you to control a big flow, a lot of flow of water, right? Understand? And of course, the more flow that we have to control, the bigger the valve has to be. And this is going to be the same thing true with BJTs. So BJTs, the more current they're trying to control, the bigger the transistor has to be, right? Does that make sense? So we'll show y'all some different sizes. Got them all the way down to little tiny ones. Got them down where you can't even see because they're part of an integrated circuit. So we know what a circuit is. This is the complete path for current to flow. And then we're going to start adding electronics into that circuit. And then what they do eventually, if they can get the size down small enough, they can integrate an entire circuit on a single silicon chip. And of course, these are what we call what? Integrated circuits. Integrated, Rich. Yeah, I see. So that's an entire circuit on a single wafer. And this is used to, you could tear your radio open and you'd see all types of transistors and resistors and capacitors and all inside that thing. Now, if you tear a radio open, basically you're going to see a few resistors, but you're going to see one chip. And then you'll see some power. You'll see the power section too, but because radios have been around for how long? A long time, right? And, yeah. So what we're talking about, if something is around for a long, long time, eventually to reduce the cost, they're going to start integrating most of the components into onto a single chip. So, but it's still not going to do away with your power transistors. So you'll still have those probably mounted to the back of the radio, and they'll be heat sinked back there. So basically, transistors are electrically controlled valves. We have two categories. We have bipolar junction transistors. Uses a small base current to control a proportionally larger emitter to collector current. So what we have, and this will probably be on the next slide, is we give these leads names. So these are going to be 3-lead devices. And this one that's got the arrow on it, so we got two symbols. We got one where the arrow points in toward this, and then you got one where the arrow points out. And you can kind of remember this, not pointing in, so that would be the symbol for an NPN, sorry, and this is pointing in. We can't get another P. So this is a P. That's the symbol for a PNP. Now, what turns them on depends on how we bias them. This lead here, this is called the collector. This lead is referred to as the emitter, and this lead is referred to as the base. So your main current valve is right here. And the base is what we're doing. The base is what we're using to control the valve. And we're controlling it with a current. But what we're going to do is we're going to take a little, real small base current to control a lot of current between your collector and emitter. So this is like the handle on your valve, right? So we get a mechanical gain on the handle on the water valve. Here we're getting an electrical gain on this. And by the way, the gain is called beta, and we'll look at that. So that means if we got a transistor that's got a beta of 100, I could put 1 milliamp of current flow here, and we would be controlling 100 milliamps of current over there. So we get a real large gain from our base to there. That makes sense? Everybody okay so far? Okay. So what we do with bipolar transistors is we can control the flow between the emitter and the collector with how much current we put into the base. Now, field effect transistors, we use a voltage to control the leads. So on a field effect transistor, so this would be what we call an N channel. And then this right here would be comparable to the collector. They're not the same, but this is called the drain. And this right here is called the source. But what we do on this guy is we control the flow of the current flow with a voltage that we put on the base. And we'll look at, not on the base, on the gate. I got to name that one. So that's about all we'll talk about on FETs right now. This chapter deals basically with bipolar junction transistors. So what are we going to use? We're going to use a small base current to control a larger collector current. So constructed of 3 doped semiconductors that produce 2 p-n junctions, and this is how it got the name bipolar transistor. So we have the emitter, the base, and the collector. No, yeah. So this, if it's an NPN, then this is N. So this is used in a pentavalent. This would be a P, so this is used in a trivalent. This is N. I'll put a P up there. Penta, P-E-N-T-A. And this would be a trivalent. It's just like the diode, the way we dope the diode to make a P material and the way we make an N material. But here what they're doing is they're sandwiching another junction, another material inside the center. And of course, this would be another pentavalent, which is the same as a diode. So a diode, a P is a trivalent, right? And N's are pentavalents, no matter how you do them. So later on, we'll get into something called a thyristor, which that sucker's got 3 junctions, right? You understand? But it's gonna go between P, N, or something like that, right? But a P would still be doped the same way as an N would be doped, right? I mean, and it's really neat the way they make these things. It was actually invented by Bell Laboratories by 2 guys. They actually won the Nobel Prize for Physics for making this thing. So this is basically what it looks like. And then we would have connections to this. So these would be the leads. This would be the base lead, base ridge. This right here would be the emitter. And then this would be the connection to the collector. So these are going to be 3-turn devices. So every one of them, guys, most of them are going to come up and they're going to have 3 leads coming out of them. And we'll show you how to identify which one's the electrical, and they can move it around those leads. So some of them, the base might be over here and the collector, the emitter. So, and we'll show you, you can identify the leads with an ohm meter, or you can look up the data sheet on it. Are we okay? This makes sense? You're looking kind of confused, Brian. Oh, you're in pain? Okay. This picture, I don't know if this picture's in the book or not. I don't know exactly where I got this from. So we know we have 2 types. We have an NPN and a PNP, right? 2 N regions separated by a small p, and PNP is 2 p regions separated by a small n. The NPN transistor is the most common, because normally we run an NPN transistors normally run with a positive power supply. Normally, we can bias it a little different, and a PNP is normally ran with a negative power supply. So that's normally, right? So the NPN is by far the most widely used. So the way this thing works is the emitter is heavily doped, the base is lightly doped, which means they have few majority carriers. Then the collector is moderately doped, so they're all doped different methods on how they come up and how they introduce different impurities into the matrix. The PN junction joining the base region and the emitter region is called the base emitter junction, and then the junction that's between the base collector is called the base collector junction. So we give these junctions names. And the way we make these work, we have to bias these junctions, right? You understand? So what is bias? That sounds like a good test question. In semiconductors, what is bias? Huh? Well, that's the way we would use a resistor to bias, but what is bias in semiconductors? This is a DC voltage. Yeah, these are DC voltages applied to a semiconductor. To set or establish determine PRE, is it PRE or parameters? I think it's PRE. No, it couldn't because it's parameters, right? Somebody spell parameters. P-E-R. There you go. So diodes, we can only we can forward bias it or reverse bias it. So if we forward bias it, it does what? It conducts. If we reverse bias it, it cuts off. But these are seen as DC voltages, even though we put an AC circuit on it. It's just that we put an AC voltage on it. One alternation is going to be seen as a positive DC, right? Which might forward bias it, but the other one's going to be seen as a negative DC at the same time. So p-n junctions, the p-n junction joining the base region, the collector region, is called the base collector junction. And so this is what we're going to establish how we forward bias this thing. And these are the names that we're going to be using for these junctions. Are we okay? Here's two symbols. And to keep up with them, these are little terms that we sometimes use. NPN is not pointing in. So if I'd come over, I'd say, and we're looking at this guy right here because this is the emitter, and this is pointing out, so it's not pointing in, right? And then this guy right here is what? This is pointing in. So this is going to help us to identify the polarities. So this right here we call the base what? We call this the base to emitter junction. And we're going to call this base collector. And that's what we're going to say when we talk about what do we need to do to cause this thing to conduct. Yeah, this is base to emitter. I should have wrote it down. I just used abbreviations that they did. Junction, right? I've run out of room. And this would be the base to collector junction. So why we're going to do that? Because when we in calculations we'll call it voltage BE. So that would mean the voltage what base to emitter, right? And then we'll call this VBC. This will be voltage base to collector. Another one we're going to look at is we're going to look at the voltage EC. What do you think that would stand for? Good. What's that? I think it's not EC. Sorry, I got that backwards. CE. DCE. This tells us how much voltage the transistor is actually dropping. So what would happen if I come over and hook up a circuit like this, and this guy right here is, and I get my load right here across the transistor. Well, if this resistor is dropping 4 volts, then and we have 12 volts applied, then voltage collector to emitter would be equal to what? 8 volts. And that would tell me, okay, I got 8 volts on the output. So depending on how you hook your output, you can hook your outputs in series with the transistor, or you can hook it in parallel, and that depends. So voltage CE would tell us, are you okay? Yeah. So that would be this would be voltage collector to emitter. And there's a rating on the transistor also that says if you get it's a breakover voltage. And so if you exceed the breakover voltage on the transistor, it's gonna mess it up, right? You understand? And that's going to be the voltage across the transistor, because that's the amount of voltage it's going to drop. So it's VCE, not VEC. In order for the transistor to operate properly, two p-n junctions must be supplied with external DC voltages to set the operating conditions, and we call this what? Bias. So to make this thing work, we're going to have to forward bias. We're going to forward bias the base to emitter. So that means we're going to have to make the base positive in respect to the emitter. That makes sense? And we got to forward bias it. If it's a silicon transistor, to make it start conducting, we're going to have approximately what for silicon? 0.7 volt. Yeah. So if I don't hit that forward bias and get it conducting, then we have no base current. If we have no base current, basically that means the transistor is cut off. Now, as soon as I come over here and I get enough current, I get enough voltage there. So it's going to be hard to get 0.7 of a volt exactly. So normally we would put a resistor right there, and then I'd come up here and I would put some voltage over here, like 5 volts, and then I would figure out what size resistor I need to drop around 4.3 volts, and then we'd have current flow. Now the current flow is going to be in this direction right here, right? Because this is a watt. This is an NPN. So now that junction would be forward biased. That makes sense. Just a regular diode right there, guys. We forward bias it, we have base current. We reverse bias it, we don't have any base current. If you don't have any base current, the transistor turns off. Yeah, when you have a base current. You have to have a base current, so you have to forward bias the base to emitter junction. Well, on a NPN, on a PNP, we would have to make it negative. So I'd come over here and I would make my base. And this is why we say PNPs normally run on negative supplies. And so now the current, now I'd have to put enough voltage over here. I'd size a resistor right here to drop what? 4.3 volts at whatever current we'll look at later on. And now we'd have current flow like this. Goes negative to positive, right? So it all depends on whether you're using an NPN or whether you're using a PNP. But once you forward bias that junction in there, and just like you would forward bias a regular diode, then this transistor is ready to turn on. Now what we do, and this is what gets people confused because we have an N right there, but what we do is we come up here and we make the C a lot more positive than the base. So that means this guy's reverse bias because the base is negative with respect to the collector. So that means we have no current flow except for leach's current. There's no current flow between the base and here. Just a hair, because we know because there's a path through there, but the only thing that's going to be through there is a very small leakage current that normally we just ignore. Because it's so small, we don't know. So technically, if this was a perfect diode, there is no current flow between the base and the collector. But what you got is you got that base. The base region is lightly doped. That means it don't have a lot of majority carriers. So all these ends come flying in here, and there's not enough holes to handle all the electrons that we have flying in from the emitter. Now you're saying, okay, here I've got all these electrons moving, and I'm looking for a positive. I'm looking for a positive, and up here on this collector is a what? It's a big O positive, not a little positive, a big O positive. It's a lot more positive than the base. The base is sitting over here in 0.7. That collector up there might be sitting at 15 volts. And those electrons are looking for what? A positive. So about 99.9% of the current flows through there. And what that's going to be controlled with is base current. So the less base current I put in, the valve closes, which means it lets less current go through. The more base current I put in, the valve opens until we get it wide open. Once we get it wide open, you can't open a water valve more than what? Than wide open. So we have two regions we can operate this in. So we operate it in what we call saturation. And what would saturation be? This means that sucker is acting like a closed switch. That means we come over here, it's acting like that. Now it's going to drop a voltage because it's not a switch, right? So if I put enough base current on there to open this valve wide open, then that sucker is going to act like a closed switch, right? Now it acts like an open switch. So we use these things all the time to control things. So I can come over here and touch a little tiny button on my car and crank my car, right? You understand? Well, I got to get some type of current gain out of something, right? And we're doing what? We're acting like open switches and closed switches. So what we can do with a transistor is I can take a very small base current to control a lot of emitter to collector current. So now it allows me to come up here and touch something, right, touch something and control a lot of current, or bring in something like that's got an antenna sticking up in there, right? You understand? How much energy do you get off the antenna on your car coming into your radio? Almost nothing, right? You understand? But yet we have these 500 watt amplifiers we can put in our car. Why? Because we can take a real small thing and bring it into something and get a lot of gain out of them. Now, if we operate it between saturation and cutoff, this thing acts like one of these. And what's that the symbol for? Rio, you're close. Rheostat. So in between saturation and cutoff, it acts like a rheostat. And what do we use a rheostat for? We use it to control current. So if we saturate it, it acts like a closed switch. If we cut it off, it acts like an open switch. In between there, it acts like a rheostat. But we can control the knob on that rheostat. We're not controlling it with somebody coming up here and doing what? Turning a knob. We're controlling it with base current. And we can control it precisely. So these are your amplifiers. These are your analog amplifiers. These are your power amplifiers. We're operating those suckers as a rheostat. Digital, we operate them in digital if we want to turn things on and turn things off. And how many times do y'all turn things on and turn things off? Yeah. Now we can turn our lights off and on with our cell phones if we buy the little units, right? And you're controlling a lot of amps there, guys. You know, up. So off and on, these are saturation and cutoff. They act like a switch, and then in between, they act like a rheostat. That makes sense? So over here, this guy would be the same thing. I mean, this guy over here, so if this was negative, this guy over here would be a big negative, right? You understand? Yep. I'm sorry, this is more negative. I drew it. So what we're going to do is we're going to forward bias the base to emitter, and we're going to reverse bias the base to collector. And the collector voltage is going to be a lot higher than the base voltage, right? That makes sense? In fact, base voltage is going to be around what? Once it starts working, it's going to be around 0.7 of a volt. So what we're doing is we're controlling the base current with this. Right now, we're controlling that base current with that resistor right there. So what happens if this voltage goes up, this guy here is dropping about what? 0.7 volts. So if this voltage goes up, let's say it was setting at 5 volts, it goes up to 6 volts. Now this guy right here is not dropping 4.3, it's dropping 5.3. The resistor's fixed, right? You understand? If the voltage goes up, if the voltage goes up, then what's got to happen? The current's got to go up. If the current goes up, that's controlling the base current, so base current goes up. If the base current goes up, then the valve turns on more. So what I can do now is I can control this with a voltage. So what would happen is I would come over here, if I could do this, and then I could come over here, and how would I convert a current into a voltage? Yeah, we did it with our sensors, because that's what we're doing. We're over here. We're making this thing act like a watt. If we're in between the center, so a rheostat. Okay. Now, if I was to come over here right here, and I was to come over here and have a variable power supply. No, we can't. So what am I doing? What am I doing right now when I come over here? But if I came over here and looked across this resistor right here, uh, you understand? I would come over here. If this was 12 volts, how much would that resistor right there drop? This, huh? How much would this voltage drop? How much would the rheostat drop? Huh? It'll always drop 12 until we exceeded our power supply, right? You understand? But what I want to do is I want to get a voltage out of this circuit right here. So we do the same thing that we did with our transistors. So I've got something that changes its resistance with base current. But what I want to do is I'm going to come over here and I'm going to add a secondary resistor right here. I'm going to add a fixed resistor right there. And then I'll come over here and I'll put my transistor right here, because that's what it's doing. It's acting like a rheostat, right? You understand? And then I would come over here. This can't be AC, by the way. And we'll talk about this later, because what would happen if it was true AC, every time it went negative, the transistor would cut off, right? You understand? So what we're going to have here, what we'd have to bring into here is we would have to bring in, if this was 0, we would have to bring in something like this. So what would happen when this is DC, it's just DC changing at its AC rate. So it would be like we did before. So if I came over here and this went up to 6 volts, then what would happen is the transistor would turn on more. What would happen if I take my output right there? So if the transistor turns on more, so if I came over and did this, let's say I put 20 volts right there. And I'm taking my measurements right here. What would happen if I made this guy, so let's say I come over here and this is going to be fixed. So we'll just make up something, let's say 10K. 10K, Rich, 10K. And this right here was 10K. And what would be my output voltage if I measured across my rheostat? It'd be 10 volts. How'd you come up with that? It's the same in a series circuit. Good. And all the voltage has to be dropped in the circuit, right? So what would happen if I change this down to a 5K? We could calculate current, but there's a lot faster way to do it. We can use what we call a voltage divider formula. And since we're only using 2 resistors, a lot of times you can do this in your head. So what would be, I want the resistance across this, so it's the resistor, so it'd be 5K, divided by total resistance, which would be what? 15K. Right off the bat, I know the K dropped. I know the K is dropped, right? You understand? And then I know that resistor is going to drop. Instead of dropping 1/2, it's going to drop 1/3. Then I would come up here and I'd multiply it by VS, and that would give me the voltage. But right off the bat, I know right off the bat in my head, I know that drops 1/3, right? So what happens to the voltage? The voltage, is it going to go up or is it going to go down? It's got to go down, right? Because if one resistor drops less voltage, then the other resistor's got to drop more. So that means if that bottom resistor is dropping 1/3, the top resistor's got to be dropping 2/3, right? You understand? So what would that voltage be? What do you say, Brian? 6.66 or 6.7? So what happens if I come over here and this input voltage goes up, which causes the transistor to cut on more, my output voltage is going to go down. But what we'd end up with over here, we might end up with something like this, and over here we're putting in something like this because we get a big current gain, right? That makes sense? Oops, I need to draw that backwards. So the output on this arrangement would be 180 degrees out of phase with the input. Does that make any difference? Well, as far as sound goes, it makes no difference at all. As long as your right channel and your left channel have the same phase shifts to the circuit. Don't make any difference. So what determines what sound you hear? Y'all know y'all listening to AC, right? I didn't know that. Yeah, that's what voice here. Your brain, your ears are taking sound waves. But what we have to do on stereos is what we have to take electrical signals and convert them into sound waves, right? So what are we hearing? Well, what we're hearing is we're hearing a bunch of stuff like this, and then we come over here, and then we have higher frequencies, and then we have lower frequencies, and so all these are composited together. So if you ever seen voice, it's all over the place. It's like this, but it's still only what? It's still only AC. It's just that there's a bunch of signals composited together. And this is what you send to your speakers, so your speakers see AC. So if I was to take this oscilloscope and hook it on your car speakers, you'd see audio, but it would be AC. It's not DC. And if I get a phase shift on my left channel, and then I get a phase shift on my right channel, if they're the same, then we have no problems. The only thing you get problems. So if you put AC on a speaker, why do speaker terminals have polarities on them? Why do they have a plus and minus polarity on them? Will it hurt the speaker if you hook them up backwards? No. It's AC. But what would happen is one speaker, if you hook them up backwards, one speaker would be going out and the other speaker would be going what? In, and they'd cancel each other out. So that's the only reason that speakers have polarity, so you know to hook which wire where, right? You understand? Because you hook them up backwards, what would happen? Wouldn't hurt speakers. Speakers are AC. I can show y'all that. So yeah, most speakers have, huh? Well, they're constantly conflicting with these. They're constantly conflicting with each other all the time anyway. So normally, to get the best stereo, you have speakers that are designed around a certain frequency. So how many speakers does your car have in it? Yeah. So mine does too. And then sometimes we only have one, what we call a super woofer, because it's the same on both sides, right? So just because this one over here is going in and this one's going out, now you do have some speakers like in my car. Uh, I have four, but two of them are combined. So what they do is two um, they have two diaphragms on it, and then they have another diaphragm up in here. So those are combined. So I have some combined speakers in my car. But if your left channel is out of phase with your right channel, it's not going to hurt the speakers. It's just not going to be as what? It's not going to be as loud, because this guy's trying to pull sound waves in, and this guy's trying to do what? Push them in. But they're actually different speakers, left, right, right. So what we'll do on this one is we're just going to talk about the NPN transistor, because everything we say as far as bias goes, everything about we say about the PNP, we just do what? Flip it, The forward bias from base to emitter narrows the base to emitter depletion region. The reverse bias, and guys, this is nice to know stuff, but all you need to know is okay, how does this thing work? Okay, so I come up here, what do I need to do? So it's an NPN, what do I need to do? How do I need to bias that? I need to make this guy positive in respect to. Now, it don't mean this guy, it don't mean this guy don't have, and this is what we make sure you understand about diodes. We don't say the cathode has to be negative and the anode has to be positive. It's all what? In respect to. Yeah, so I could come up here and I can put a little p right there. I mean, a little plus right there. And this right here could be a little more plus, right? As long as it's what? About 7/10, right? And then over here, this guy here is going to be a big plus. So if this is a little tiny plus and this is a little bigger plus by 7/10 of a volt, then this guy here can forward bias. And we're going to see this a lot because of the problem we have with temperature and p-in junctions. What problem do we have with temperature and p-in junctions? The more we lose control of them, right? So we have a way that we can compensate for that, and we'll try to show you that. So this is what I've already drawn, right? So here we're using two battery bias, and what we would do is we'd make this one variable, and then this right here is going to be fixed. So I'd come over here and we can make it, as long as we don't exceed the breakover voltage, we could come over here and make this almost any voltage we want to. So what's going to happen once we get up above around what here, around 7/10 of a volt, then we're going to start having what? Base current, right? As soon as I have base current, we're going to have what? Collector current. Everybody okay? Yes or no? Emitter to collector. Normally we call it collector current, even though you can't have collector current without having emitter current, right? Is the emitter current and the collector current going to be equal to each other? Well, look here. So I got this right here. This is emitter current. I've got this right here. This is emitter current. So emitter current is equal to base current plus the collector current. And you notice I said about 99% of the current goes this way, but that still leaves what? Yeah. Well, this is not leakage current. This is actually current. Leakage current is current that we're not controlling, right? We're controlling this thing. We're controlling that base current. So if this is the formula, E is equal to B plus C, IB. So let's do this. IE is equal to IB plus IC. Then what would IC be equal to? Let me make it bigger so y'all can see it a little better. So IE, so what would IE be? IE would be emitter current, right? Is equal to IC plus IB. Then what would IC be equal to? These, we can't divide because all we got is math. I mean, all we got is plus. So pluses might change to minuses, but pluses can't change to divide, right? There you go. You can't take this formula right here and rearrange it. I mean, so the opposite, so if I've got multiplication, when I start moving around, what's the opposite of multiplication? Division. So that means if I've got V is equal to I times R, then when I take the reciprocal, it's going to change to division, right? You understand? Yes or no? Over here, we got plus. So the only thing I can do when I move things around is come up with a what? A minus. So I can't go from a plus in an equation over to a minus in a transposed equation, right? I'm sorry, said that wrong. I can't go from a plus to equation when I transpose the equation and end up with a divide. Make sense? So the only thing when we transpose this, the only thing we got available to us is what? Yeah. So what would IB equal to? The big one. IE minus what? Let's see. Huh? The big one is which is the biggest current flow in the transistor? The collector. No, look. IE is equal to IC plus IB. Now the rest of the so look, how many current paths do I have through the emitter? I'm drawing right here. I have this one right here, right? And I have this one right here. Both of those are flowing through the what? Through the emitter. The emitter has the highest current flow in there. And that's why the other ones are minus, right? You understand? So the other ones are always going to be, what's the smallest? What's the smallest current? The base is the smallest. The only thing difference between the emitter current and the collector current is that extremely small base current. Yeah, the base is always the smallest. That's where we get our gain. This is our valve right here. And this is what I showed you a while ago. So if this thing here had an absolute beta of, if this thing here had an absolute beta of 100, that means if I put 1 milliamp over here, I would get what? I'd get 100 milliamps over there, but I would be putting 101 milliamps into the emitter. Because 1 milliamp is going to the base, right? You understand? No, it depends on the way the symbol is drawn. I mean, in a power supply, so what we can do with this guy is we can come over here and take a Zener diode. Yes. So what can I get out of a transistor? This is a current valve, guys. So we get a real high watt current gain. Now, the biggest problem we have with Zener diodes is that you just can't operate at a lot of current. But what we're using here is we're using a Zener diode to provide the base current to the transistor, and then the transistor is running the output. So over here, if this is a 5.6 volt Zener, then this guy over here would be about what? About 5 volts, but at a lot higher current. Because what can we get out of a transistor? We get current gain, but I can take that current gain and run it through a resistor and get voltage gains, right? You understand? By adding a fixed resistor. So here we're taking this little bit of current right there, right? You understand? And so if this thing had a beta of 300, then that means if I'm putting, 1 milliamp over here, I could get what? 300 milliamps over there on my output of my. And we've got another something we can do to actually really get the gain way up. So this is basically the way a Zener power supply would work is we would combine it with a bipolar transistor, because what can we get out of the bipolar transistor? A current gain, yeah. So we can run a lot heavier loads, but we still use the Zener just for the reference, right? You understand? And it regulates too, because if this voltage tried to drop down, it's going to try to maintain it's going to try to maintain around 0.7 of a volt. So if it drops down, then it would automatically do what? Turn on a little more. So here you can't say it's always on the bottom. But the emitter, the error will always be what, Bernard? It'll always be the error. Yeah. But we could arrange this in different ways, so it depends on the schematic how you draw them. Any more questions? So these are the guys that's going to give us our gain. These are the guys that are going to take these little tiny signals that we're getting off an antenna, right? That's way down in what we call, microwatts worth of power, and we end up pushing, a couple hundred watts coming out of these speakers if you got a power amp. Most regular just standalones, I don't know, I need to look at mine. Used to be around 23 watts out of a radio without installing a power amp in your car. Okay, guys, y'all take a break and we'll come back and talk about the first part of test 2 since most of y'all are here.